Welcome back to the deep dive. We are, once again, ripping the covers off some really dense source material, turning these complex industrial specs and engineering blueprints into clear, actionable knowledge.
And we are really getting into it today.
We are. Today, we're strapping in for, well, a masterclass in system architecture. We are tackling one of the toughest, dirtiest, and frankly, most overlooked engineering challenges in the entire heavy vocational sector.
A concrete mixer truck.
The concrete mixer truck.
It sounds like a pretty mundane topic, I know, but the technical document we're synthesizing today is, it's anything but. It's a massive, critical, technical specification report.
And it's written from the perspective of a top-tier automotive consultant, right? The kind of firm that basically writes the rules for entire industries.
Exactly. This report is essentially the complete engineering blueprint for dragging this whole segment of heavy machinery, kicking and screaming, into the electric age.
Okay, so let's jump right into the deep end, because the core problem driving all this investment is just staggering, demonstrable inefficiency. If you look at a traditional diesel concrete mixer, what is the single most polluting, wasteful thing it does?
The word is idling. It is the chief offender. Concrete mixer trucks are just notorious pollution and noise sources, especially when they're operating right next to residential areas or on these tight urban construction sites.
And the source material highlights a really staggering statistic here.
It does. The main engine on a traditional diesel mixer might be idling for up to 50% of its total work time, sometimes even more.
Just to keep that drum slowly rotating.
Purely for that. That's half its functional life spent burning fuel, creating noise, and fouling the air.
And here's the inefficiency paradox that the report really drills down on. Maintaining that minimum, that low-speed rotation of the mixing drum, it only takes about 20 to 30 kilowatts of functional power.
Right. But to provide that power through the old mechanical power takeoff system, you're forced to run this massive 150 to 300 kilowatt diesel engine at its absolute least efficient operating point.
It's the dictionary definition of overkill.
It really is. It's like using the full power of a Formula One engine just to turn a low-power cooling fan.
Yeah.
I mean, the regulatory and economic pressure to eliminate this is just immense.
So that brings us to our mission statement for this deep dive. We are going to unpack the complete engineering blueprint for solving that exact problem.
We're looking at the full system integration needed to implement a P2 hybrid architecture.
Combined with electric power takeoff, or ePTO, on a really robust dual voltage 24-volt and 400-volt platform. And we're focusing specifically on the motor and control specifications, following the consultant's own deliverables.
This conversation is your absolute shortcut to understanding the full system integration capacity required to make this multi-billion-dollar transition work.
So let's start not with wires and circuits, but with the strategic rationale. I mean, why are manufacturers being forced to spend billions redesigning these workhorse vehicles?
Well, this shift isn't optional. It's driven by severe, hard and fast global regulations that are slamming the heavy-duty vehicle market right now.
Okay, so what are the key regulatory deadlines that are driving this forced evolution?
The regulatory landscape is the true market driver, period. In Europe, the mandates are easily the most aggressive. The EU is demanding a 90% CO2 reduction for heavy-duty vehicles, or HDVs, by 2040.
And the interim targets are what's forcing the action now.
Exactly. You've got a 15% reduction by 2025 and 45% by 2030. These are forcing design choices right now. This isn't about, marginal improvements. It requires a complete fundamental overhaul of the drivetrain architecture.
And what makes this regulatory wave so different from all the previous ones is that the focus has shifted, right? It's not just about the tailpipe when the truck is on the highway anymore.
That is the critical pivot point the consultant emphasizes. The new Euro 7 standard and the UN GTR No. 22 regulation are fundamentally changing the game.
How so?
They're bringing non-motive energy consumption into the regulatory evaluation for the very first time. Before, regulators didn't care how much power you used to run the hydraulics or the mixer.
But now?
Now, the energy used to spin that drum is calculated into the vehicle's overall efficiency and emissions profile, and that single regulatory change makes highly efficient ePTO development an absolute necessity, not a luxury.
And then you have the local barrier to entry. We're seeing this proliferation of ultra-low emission zones, or ULEZ, in major cities across Europe and now North America too.
Right. If you can't operate purely electrically on the job site, quietly and without emissions, you simply cannot bid on the contract. It's becoming a literal license to operate in densely populated areas.
So the electric capability is the ticket in.
It is, and the sources underscore that noise regulations are just as crucial as the CO2 limits. For instance, the Dutch PX standard mandates that nighttime delivery vehicles operate below 60 to 65 dBH.
Which is pretty quiet for a construction vehicle.
It is. And the traditional mechanical and hydraulic PTO systems on mixers, they generate this high-frequency ear-splitting whine that immediately fails to comply. Electrification of the work function is the only way forward.
Okay, let's turn to the other two major global markets mentioned in the report, the US and China. They're pushing electrification hard too, but maybe through different mechanisms.
Correct. In the U.S., you have the Advanced Clean Trucks, or ACP, regulations. California is leading, but it's expanding. They push manufacturers toward these really ambitious zero-emission vehicles, ZEV, quotas.
And for city delivery trucks specifically.
The U.S. goal is 60% ZEV sales by 2032. Now, a P2 hybrid is a transitional technology, but if it's a plug-in hybrid or a range-extended vehicle using that ePTO function, it gains significant credit toward those ZEV quotas.
So it's a lower risk path to compliance than going full battery electric right away.
It's a very viable path, and they also demand compliance with the SAE J1939 communication protocol for all that data exchange.
And China, as the world's largest market for, well, everything, including these trucks.
China uses a mix of regulatory and incentive strategies. They have dual credit policies, which are a bit like fuel economy and emission credits. And critically, they provide road priority advantages and registration benefits for new energy vehicles.
So they're really pushing it.
They are. While China supports pure battery swapping and hydrogen fuel cells, for the existing massive fleet of concrete mixers, the P2 hybrid architecture is just the most pragmatic, reliable choice. It completely avoids the operational headache of range anxiety.
And it uses the existing, very deep supply chain of robust engines and transmission.
Exactly.
Okay, let's unpack that P2 hybrid architecture itself. For those who might be new to hybrid layouts, where does the motor actually sit, and how does that placement achieve this functional separation we call decoupled ePTO?
Right. So P2 architecture is named because the electric motor is physically placed in the power flow at position 2.
Which is where?
That's between the engine and the transmission. This placement is absolutely fundamental because it allows for the use of the K0 clutch.
The decoupling mechanism.
It's the critical decoupling mechanism. This clutch lets the system completely isolate the engine from the rest of the drivetrain.
So when we talk about a decoupled ePTO, what's the core functional separation that's being achieved?
It's the crucial separation of the mixing function from the engine speed. Think about the old system. The PTO was a mechanical drive taken directly off the gearbox.
So drum speed was tied directly to engine speed.
100%. If the driver had to rev the engine to move the truck a few feet, the drum would instantly speed up. If the engine idled lower, the drum slowed down.
Which, as you mentioned, is terrible for the concrete's integrity. It leads to segregation or inconsistent slump.
Precisely. The core value of the ePTO system is that the mixing drum is driven by an independent e-motor powered by the high-voltage battery. That separation eliminates the link between vehicle speed and drum speed.
Total control.
Total control. You program the system to maintain a constant 1.5 RPM for agitation, and the motor control unit uses sophisticated algorithms to guarantee that speed no matter what the diesel engine is doing. It's a massive quality benefit.
This leads us directly to the technical logic of the dual platform.
Yeah.
Why 24 volts and 400 volts? Why do we need two electrical systems running at the same time on this truck?
It's not just redundancy, it's necessity. It's born of physics, safety, and frankly, robustness. A system this large in this kind of environment cannot reliably or safely run everything off a single voltage platform.
Let's focus on the high voltage side first. The report specifies 400 volts, often running up to 450 VDC. Why that specific voltage range?
The 400V high voltage platform is where the real power delivery happens. It's dedicated to the traction motor and, critically, the high power ePTO motor. As we established, a large 12 cubic meter drum needs immense instantaneous power, often peaking between 80 to 120 kilowatts.
And if you tried to deliver 120 kilowatts at 24 volts?
You would have catastrophic losses and massively heavy wiring. This is where physics dictates the engineering. High voltage is required to minimize joule loss.
That's the heat generated in the wiring.
Exactly. It's proportional to the square of the current, I squared R. So if you double the voltage, you have the current for the same power, but you actually quadruple the loss reduction.
So by operating at 400 volts instead of 24, you dramatically lower the current. That reduces heat loss, allows for much thinner and lighter cables, and improves overall energy use for the battery.
Yes. The cost savings in cable material plus the improved system efficiency more than justifies the added complexity and cost of the HGV components. The typical working range is between 270V and 450V DC, which allows a wide buffer for the battery SOC and any transient voltage events.
And the 24V low-voltage platform, this is the legacy workhorse system. But why is it still functionally critical in this new hybrid design?
It's the lifeboat. The 24V platform powers all the safety-critical functions. The Supervisory Control Unit, or SCU, that manages the whole truck, all the sensors, lighting, and the crucial electromechanical assist systems like steering and brake assist.
And this is required under ISO 26262 functional safety standards.
It is. The core principle is redundancy. If the 400V system suffers a catastrophic, unrecoverable failure, say a short circuit or an inverter failure, the vehicle must still maintain basic functionality. The driver has to be able to safely pull over, operate the brakes, and maintain basic lighting.
So the low-voltage side manages the brains and the minimal safety features, and the high-voltage side provides the muscle for moving the truck and spinning the drum. It's a beautifully balanced architectural approach.
It is, and connecting them is the DC-DC converter. This critical component takes power from the 400V battery system and steps it down, charging the 24V battery and maintaining the health of the low-voltage control platform. It's the bridge that ensures the safety net always has power.
Okay, now we move to the heart of the hardware. The motor itself. This is detailed in Section 4.1 of the consultant's report. This can't just be any off-the-shelf unit, can it?
Right.
We're talking about matching the motor to a uniquely challenging load profile.
Right. And the challenge, as our analysis confirms, it lies in the material itself. Concrete is what engineers call a non-Newtonian fluid.
Specifically, a Bingham plastic.
A Bingham plastic, yes. We're all familiar with Newtonian fluids like water or oil. Their viscosity is constant. A Bingham plastic has a yield stress. It behaves like a rigid solid until you apply a specific amount of force, and then it flows like a viscous liquid.
So when the drum stops, the concrete is essentially gluing itself to the drum walls, and the motor needs a massive instantaneous shock of torque to overcome that initial glue and get it moving again.
Exactly. This is why the motor must be capable of handling these severe, nonlinear, and highly momentary load spikes. The report breaks down the critical load states.
Let's run through those numbers.
Okay, first, full load startup. This is the most demanding scenario, especially if the truck's been stationary for 20 minutes. The peak drum torque needed can reach 60,000 to 80,000 Newton meters.
Wow. And that's just for a few seconds.
For less than 10 seconds, but the motor has to be engineered for it. Then you have mixing charging mode. This is at the plant when you're mixing fresh concrete. Rotation is faster, 10 to 14 RPM, and the drum torque is still substantial, 30 to 45,000 Newton meters.
And the third mode is the most common one.
Right, transport agitating mode. This is the marathon mode. The drum rotates very slowly, typically 1 to 3 RPM, just to prevent segregation. The torque drops to 15 to 25,000 Newton meters. The key takeaway here is that this mode represents over 80% of the vehicle's operating time.
And that statistic is crucial, isn't it? 80% of the time is spent in a low-speed, lower-power mode. That has to dictate the whole motor selection and optimization strategy.
It absolutely does, because efficiency in this specific regime is the key to battery range and operational cost savings.
So how do we match a high-speed electric motor, which likes to spin at thousands of RPM, to the drum's requirement of, 1 to 14 RPM?
By using a massive gear reduction.
A massive one.
A massive one. The system relies on a multi-stage planetary gearbox. The consultant report specifies that typical gear ratios for this heavy vocational application range from 100 to 1 to 140 to 1. If we take, say, I-130 as a benchmark example, that's a common commercial standard, we can calculate the required motor torque.
Okay, let's run those numbers from the report. If the drum needs a peak of 75,000 Newton meters, what does that translate to at the motor shaft, assuming a pretty efficient, maybe 95% gearbox efficiency?
When you divide the drum torque by the gear ratio and factor in that efficiency, the requirement at the motor shaft translates down to about 607 Newton meters. But, and this is important, the consultant strongly recommends building in a significant safety margin. We're talking 30%.
To account for worst-case scenarios.
For absolute worst-case scenarios like partial setting or extreme ambient heat. So the required motor peak torque is defined as 800 to 950 Newton meters. The continuous or rated torque for that long-duration mixing mode, that has to be around 350 to 400.
Which brings us to the technology decision. Permanent magnet synchronous motor, PMSM, versus an induction motor. The consultant's strategic decision is unequivocally for the PMSM, specifically the interior PMSM, or IPMSM. Why that specific technology?
The justification is entirely rooted in that dominant transport mode we just discussed, that 80% operating time window.
So what are the clear technical advantages of IPMSM here that swing the decision?
Okay, there are three. One, superior low-speed efficiency. For the vast majority of operation, the IPMSM is vastly more efficient than an induction motor, which suffers significant losses at partial load and low frequency. That efficiency directly translates into more zero-emission operation time.
Better range in those ULEZ zones.
Precisely. Two, higher power density. Heavy trucks have limited space. PMSMs offer 4.0 to 5.5 kilowatts per kilogram, which far exceeds IMs. This reduces the size and weight of the whole ePTO unit, which increases the truck's effective payload, a massive economic benefit.
And the third advantage.
Reluctance torque utilization. The IPMSM design is clever because the magnets are embedded internally. This allows the motor to leverage reluctance torque. Think of it as getting a free magnetic boost from the shape of the rotor itself. This boosts torque output without just cranking up the current, which minimizes the crucial copper loss.
So it's not just about raw power. It's about power packaged densely and delivered efficiently at exactly the point the truck needs it most. Low speed, continuous torque. What are the physical specs the consultant recommends for this rugged application?
We are looking at a robust, liquid-cooled IPMSM package. Rated power of 60 kilowatts, peak power up to 120 kilowatts, rated torque at 350 to 400 newton meters, with a max speed of 3,000 to 3,500 RPM.
And the protection ratings are critical.
Absolutely. Given the high heat, vibration, and just the abrasive environment of a construction site, it has to have Class H insulation, rated for 180 degrees C, and an ingress protection rating of IP6K9K.
IP6K9K is extreme. That means it can resist dust ingress and high-pressure, high-temperature washdowns. That really speaks to the real-world operational environment, doesn't it?
It has to survive being cleaned with a power washer blasting hot water. That's just standard procedure at any construction yard.
Let's now do a deep dive into the efficiency map. This is the North Star of the motor design. If efficiency is the goal, what are we trying to achieve with the shape of this map?
The goal is to make sure the motor's highest efficiency island, the zone where efficiency is 96% or higher, ideally pushing 97, perfectly aligns with the concrete mixer's most common work region.
Which is that 102,000 RPM range.
Exactly. That core working region corresponds to motor speeds of about 1,000 to 2,000 RPM and torque between 150 and 300 newton meters. This covers the most frequent mixing and unloading modes where energy consumption matters the most.
So to understand how to get that peak efficiency, we have to look at the losses and the physical design choices that combat them.
Right. There are two dominant loss models we need to minimize through physical design. First is copper loss, I squared R. This loss is proportional to the square of the current, and it dominates during startup or heavy mixing, low speed, high torque.
And how do you fight that?
To minimize this, the design must use advanced techniques like hairpin windings. These are rectangular conductors instead of traditional round wires. They pack more efficiently into the stator slots, which increases the copper area, reduces the DC resistance, and thus drastically lowers the I squared R loss.
Okay, and the second loss?
That's iron loss, or PFE. This loss dominates at high speeds and high frequencies. It's caused by the energy needed to repeatedly magnetize and demagnetize the core material. This is minimized by using high-grade, low-loss silicon steel laminations that are as thin as possible.
So the optimization strategy isn't just about the peak efficiency number. It's about optimizing the entire operational envelope, particularly that low-speed end that accounts for 80% of the time.
Exactly. The low-speed zone, corresponding to that 1 to 3 RPM transport mode, which is 300 to 900 motor RPM, has to be optimized. Here, the copper loss is managed, but we also have to minimize things like cogging torque, that slight magnetic pull that resists rotation even with no current. Keeping efficiency above 85% in this low-power zone is achieved by clever control strategies.
Which leads us perfectly into our next section. We've established that the motor hardware is only as good as the software driving it. This takes us into control technology, and the foundation, as specified in the report, is field-oriented control, or FOC. If FOC is the algorithm's soul, how does it work?
FOC is the standard for any high-performance PMSM control system. It's a mathematical transformation that lets the controller treat the complex three-phase AC motor like a simple two-axis DC motor.
It simplifies it.
It simplifies it for control. It decouples the stator current into two orthogonal components, the flux component, ID, and the torque component, IQ. This allows for independent and precise control of the magnetic field and the resulting torque, which is essential for dynamic load control.
And within FOC, the report highlights a critical torque generation strategy.
Yeah.
MTPA, maximum torque per ampere. Why is this mandatory, especially for the IPMSM we selected?
MTPA is mandatory because it's the ultimate energy saver. Since we're using an IPMSM, we have those internal magnets and the benefit of that reluctance torque. The MTPA strategy forces the controller to find the optimal current vector, the ideal balance between ID and IQ that produces the required torque using the absolute minimum current.
So it's about drawing the smallest possible current to do the job?
Yes. Think of it as always finding the path of least resistance. By minimizing the current, you directly minimize the copper loss, I squared R. This drastically minimizes heat generation, protects the motor, and maximizes that precious battery range. A motor that isn't running MTPA is just generating excessive heat and wasting energy.
Let's talk about precision control. This is a heavy, sloshing drum of concrete. How does the system ensure robustness and stability, especially during delicate maneuvers like zero-speed holding or startup?
Precision starts with position sensing. You can't use delicate sensors here because of the environment. The system must use a resolver.
Which is essentially a robust rotary transformer.
It is, and it's mandated in the specification because, unlike optical encoders, a resolver is fundamentally resistant to high temperature, severe vibration, oil, dust, and washdowns.
And that position accuracy is crucial for safety.
Absolutely. The resolver is critical for robust zero-speed and startup control. If the motor control loses the exact rotor position under a 75,000 Nm load, the controller might apply current at the wrong angle,
causing an unintended reversal or a violent lurch.
Exactly. That hardwiring position feedback is the first layer of defense against mechanical damage.
In the core function of the ePTO system, what sets it apart from the old mechanical PTO is the speed closed-loop control. This is what guarantees the concrete quality.
That's right. The system must maintain constant speed logic. The MCU, the motor control unit, runs a multi-level PID controller. The outer loop monitors speed, taking the target, say, 1.5 RPM from the SCU. The inner loop monitors current. The system must guarantee that 1.5 RPM is maintained precisely.
Regardless of engine speed, road bumps, anything.
Regardless of anything, this consistency is the foundation of quality assurance for the concrete.
And how does the system manage the severe dynamic load fluctuations from all that concrete sloshing around inside the drum?
This is where the advanced algorithms truly pay for themselves. The specification mandates active damping algorithms within the speed control loop. The sloshing mass creates these severe, low-frequency but high-amplitude periodic load-torque fluctuations.
And if that's unchecked, it can cause real damage.
It can lead to mechanical resonance and literally shake the gearbox and mounting structures apart over time. Active damping algorithms detect these fluctuations almost instantly and inject precise counter-torque signals to quickly compensate and neutralize the resonance.
It acts as a digital shock absorber for the concrete.
That's a great way to put it. It stabilizes the load and protects the expensive planetary gearbox.
This all relies on flawless communication between the brains, the SCU, and the muscle, the MCU. Let's trace the flow of command coordination.
Okay. The SCU is the high-level manager, deciding the operational mode. It sends the target speed and torque request to the MCU. The MCU then executes this request using FOC and its dual-loop PID controls. The sequence has to be tightly coordinated.
Detail that necessary state-machine coordination sequence that the consultant specified for safe operation.
The sequence ensures safety and manages large inrush currents. The MCU first checks for HV ready,
meaning all the high-voltage interlocks are verified and closed.
Right. Next, it initiates pre-charge, slowly charging the massive DC bus capacitors to avoid sudden inrush current shocks. Once the voltage is stable, the SCU sends the enable command, followed by the specific speed request via the CAN bus. Finally, it transitions to running mode.
And the stop sequence is just as important.
The crucial element is the stop sequence. It must involve soft deceleration, actively driving the motor speed down to 0 RPM before any mechanical clutches or brakes engage. This prevents mechanical or hydraulic shock to the system.
This is where the engineering really transitions from just motor control to material science. The motor isn't just a driver, it's a sensor. Tell us more about this advanced insight. load sensing, and concrete quality.
This is truly fascinating. The system transforms the mixer truck into a giant mobile rheometer. By continuously monitoring the precise relationship between the actual torque T-act applied by the motor and the drum speed, and the MCU can estimate the concrete viscosity or slump in real time.
So the system knows that the concrete is thickening even before the truck arrives at the site.
Exactly. If the control system detects that the actual torque is continuously rising over time while the requested speed stays constant, it indicates that the concrete is rapidly thickening or beginning to set prematurely. That's slump loss.
And then it can do something about it.
The SCU can then automatically adjust the agitation frequency, applying precisely calibrated torque pulses to break up the initial setting structure, or, critically, it can warn the driver and dispatcher to immediately adjust the slump or prioritize delivery. This proactive intervention prevents massive material spoilage.
And this detailed logic is all codified in the Control Strategy's white paper, deliverable 04-ARO1. What specialized algorithms does this document mandate for handling concrete-specific challenges?
The white paper defines the necessary software structure to maximize material quality. Two key specialized algorithms stand out.
What are they?
First, anti-set agitation. This is a low-speed, high-torque pulsed technology. During long trips, material tends to settle and compact at the bottom of the drum. This algorithm delivers periodic, high-magnitude torque pulses to stir the settled material without significantly changing the overall rotation speed. It ensures homogeneity.
And the second one?
Blockage detection. The system continuously monitors for abnormal, sudden increases in the IQ, the torque current, that are sustained for longer than a typical sloshing oscillation. This indicates a major obstruction or a clog.
And if it detects one?
If a blockage is detected, the SCU can trigger an automated short reverse spin cycle for self-cleaning, attempting to clear the obstruction before it causes structural damage or full solidification.
In a heavy construction environment, things break, things get hot. When a fault is detected, the primary goal, especially for concrete, isn't immediate shutdown, it's saving the product. This makes the derating philosophy the ultimate business continuity plan.
That's the core philosophy. Availability is king. If the entire 400-volt system shuts down instantly due to, say, overheating in the California desert, the entire load of concrete will solidify within minutes.
Which is a huge financial loss.
It's a multi-thousand-dollar loss of material, and it often means the drum itself is scrapped because jackhammering concrete out of a mixer barrel is an extremely difficult, expensive, and time-consuming process, so the strategy is graceful degradation.
Limit performance, but maintain minimum rotational functionality.
Exactly.
Let's look at the specific thermal derating strategy for the motor and the controller. What are the critical temperature thresholds for the winding?
Okay, we monitor the motor winding temperature, T-stator, extremely closely. Below 130 degrees C, you have 100% torque capacity available.
And then it starts to ramp down.
Between 130 and 150 degrees C, the system enters linear derating. The SCU smoothly reduces the maximum allowable torque along this 20-degree range. So even if the driver is demanding full mixing torque, the system ignores the demand and only allows the reduced derated torque.
Allowing the motor to cool down passively while still working.
Right. And above 150 degrees C, that's the danger zone. The system is forced into a protective limp home mode. Output is severely restricted, often to just 0.5 to 1.0 RPM, purely to sustain rotation and prevent the concrete from setting. It gives the driver precious minutes to safely unload.
And what about the brain of the controller, the IGBTs? They're the most sensitive power electronics.
The IGBT junction temperature is monitored to prevent catastrophic failure, or what we call blowing the stack. If the junction temp hits 120 degrees C, the system executes a protective stop switch PWM off command. The goal is immediate cessation of switching to prevent thermal runaway.
Beyond heat, power loss is also a factor. How does the system manage the battery running low?
This is the voltage derating strategy. If the high voltage battery state of charge, or SOC, drops to a critically low level, say below 10%, the SCU immediately restricts power output.
And the priority shifts.
The system's priority shifts entirely. It goes from efficient driving or high-speed mixing to just maintaining that bare minimum rotational speed, that 1 RPM, needed to keep the material consistent. It ensures the remaining battery capacity is used strictly for material salvage.
Functional safety is paramount, given the high power and the dynamic environment. Under the international standard ISO 26262, what is the highest safety goal assigned to the ePTO system?
The core safety goal is the prevention of unintended reversal. The drum unexpectedly spinning backward at high speed. Imagine the danger of that happening on a busy construction site. This risk is classified by the consultant as ASIL-C.
Automotive Safety Integrity Level C. That means failure poses a significant hazard that needs rigorous mitigation.
It does.
So how is this critical risk technically mitigated across the two main control units?
It requires tight coordination. The SCU receives the vehicle speed data via the J1939 CCVS message from the vehicle's main bus. The MCU must then have a software-enforced, hard-coded rule that inhibits negative or reverse torque commands if the vehicle speed is above a defined threshold, typically 10 kilometers per hour.
So you can't accidentally unload while driving down the road.
No, that function is disabled at speed.
Beyond mechanical safety, we have to address high-voltage safety and ECE R100 compliance. If the vehicle is in a severe collision, that 400-volt buzz is a major hazard to first responders.
Absolutely. The MCU must implement active discharge. This is a mandatory safety feature. In the event of a critical failure, like a collision detected by an airbag deployment signal or a breach in the HVIL, the high-voltage interlock loop, the system must drop the DC bus voltage.
From 400 volts down to below 60 V DC.
Within 5 seconds, that 60 volts is generally considered the safe touch voltage limit.
And the clever engineering solution here is using the motor itself as the discharge resistor. Correct. It saves weight and space.
That's the genius of it. Instead of using a separate bulky resistor bank, the MCU strategically uses the motor windings. It does this by performing a controlled D-axis current injection, essentially short-circuiting the power through the motor to dissipate the stored energy quickly and reliably.
Finally, the ultimate failsafe: redundancy. What happens if the entire 400-volt system suffers an irreversible, catastrophic failure?
This is a strategic highlight of the consultant's plan. The 24V emergency system, a separate low-power motor rated at about 3.1 kilowatts, is included. This system has its own independent wiring, controller, and power source, the 24-volt battery.
So if the 400-volt system dies,
In the event of a confirmed 400-volt failure, this system automatically intervenes to maintain minimal drum rotation. Again, just 1 RPM. It's the equivalent of a ship's emergency diesel generator, designed only to run the absolute critical systems. It ensures the concrete can be salvaged.
we've covered the strategy, the hardware, and the software logic. Now we need the concrete deliverables, the detailed documents that let the different engineering teams actually build this system. The consultant defined 4 key deliverables, starting with the communication matrix 0402, which dictates the digital handshake via the J1939 protocol.
This document is the Bible for system integration. It defines the digital language, the DBC data dictionary used between the SCU and the MCU using the heavy-duty vehicle standard, SAE J1939. Precision here is everything, especially the update rates.
Give us the core command and feedback signals that allow the SCU, the brain, to talk to the MCU, the muscle.
Okay. First, the SCU request. The SCU uses PGN 0 typically labeled TSC1, torque speed control 1. This is the command message that sends the target requested speed and the torque limit. Critically, this message must be broadcast at a rapid 10 millisecond update rate.
Why 10 meters? That's extremely fast for a CAN bus in a heavy vehicle.
The rapid rate is required specifically because of the volatile dynamic load profile of concrete. If the system had a flow update rate, say, 100 milliseconds, the control unit would lag in detecting and compensating for the high-frequency load disturbances from the sloshing.
That active damping wouldn't work.
It wouldn't work effectively. A 10 millisecond update rate gives the MCU the near real-time data needed to execute the active damping and PID stabilization successfully. A failure here means rough, inconsistent drum operation and, eventually, mechanical wear.
And the feedback from the MCU.
The MCU reports back using PGN 0-aux-004 or EC1. This reports the actual speed and the actual torque percentage. That torque percentage is vital as a negative value indicates regeneration or braking mode. This feedback must be sent every 20 milliseconds.
And diagnostics are built in.
Yes, real-time diagnostics are handled by PGN 0xSECA, the standard DM1 message. This reports things like component temperature warnings and ensures the control center is immediately aware of potential derating conditions. The specification also requires robust timeout protection. If the MCU doesn't get a valid command for, say, 100 meters, it shouldn't just stop.
What does it do?
It should hold the last valid speed for 10 seconds before gracefully slowing to 1 RPM. This preserves the material during communication glitches.
Next, the motor interface data, AS04-03, or ICD, the physical specifications. This is where the electrical and mechanical teams must align. What defines the motor's physical integrity and connection points?
Mechanically, the motor must use industry standards like the SAE J67C flange for mounting and the DIM 5480 spline for the output shaft. This ensures proper mating with the high-ratio gearbox. And the mechanical design is non-negotiable. It has to withstand massive shock loads, specified as a 2,000 Newton-meter peak torque impact.
That's the guarantee that the motor shaft won't shear off during a sudden jam.
Precisely.
And for the critical high-voltage electrical connections, safety and signal integrity are everything.
Absolutely. We specify industrial-grade, highly reliable connectors like Amphenol Surlock Plus or TEHVA 630. The mandatory requirement here is 360-degree electromagnetic shielding.
Often a braided metal sheath covering the whole cable.
Right, and it has to be securely terminated at both the motor and the controller.
Why is that shielding so important beyond just standard electrical safety?
The inverter, the MCU, is high-frequency switching the 400-volt supply to drive the motor. This generates massive electromagnetic interference, or EMI. Without complete 360-degree shielding, that EMI will radiate and disrupt the sensitive 24-volt control lines, the resolver signals, and the CAN communications.
So it could cause system crashes.
It could cause intermittent system crashes or sensor malfunctions, rendering the entire truck unreliable. It's an EMC compliance failure waiting to happen. And finally, thermal management on the motor side. The spec demands a flow rate of 14 liters per minute for the coolant, with the inlet temp limited to 65 degrees C or less.
A crucial number.
Very. If the coolant supply is insufficient or too hot, the motor will immediately begin thermal derating, crippling the truck's ability to mix aggressively.
Our final deliverable defines the MCU itself in the motor controller interface data, 0404. What defines the housing and the control connections for the inverter box?
The MCU needs to be incredibly rugged. The hardware must feature a thick, die-cast aluminum casing with that critical IP6K9K protection resistant to high-pressure washdowns and corrosion. It must also include a pressure equalization valve, a breather plug to prevent condensation buildup.
Which could cause internal short circuits.
Exactly, given the wide temperature swings this unit will experience.
What are the critical pinouts on the low-voltage connector?
The MCU typically uses an automotive-grade connector, like a 35-pin amp seal. Key low-voltage pins include KL30, which is direct battery positive for constant power, KL15, the ignition wake-up signal, dedicated CAN HL pins, and crucial for safety, the HVIL in-out loop terminals.
The high-voltage interlock loop.
That's the safety chain that must be complete before the 400-volt system can activate. If a plug is loose or damaged, this loop is broken and the system remains safely disabled.
And the requirements for the high-voltage connection itself.
On the HV side, the DC input requires robust dual-pole high-voltage contactors and a dedicated pre-charge circuit to manage inrush current. And finally, to ensure the integrity of the crucial resolver feedback, the ICD specifies the use of dedicated, shielded twisted pairs for the sine-cosine signals, operating at a defined frequency and voltage, like 7 VMs at 10 kHz. Signal integrity here is the difference between smooth control and potential runaway oscillation.
So if we synthesize the key insights from this comprehensive blueprint, what becomes profoundly clear is that this ePTO system is not just a hardware integration. It marks a fundamental strategic shift in heavy vocational vehicles.
It really does. It's a shift to software-defined hardware. The differentiation in the market is no longer about the biggest engine. It's about the robustness and intelligence of the control logic.
Meaning the competition isn't won on raw kilowatts, but on control sophistication. Things like that MTPA strategy, optimizing every milliamp of current, the resolver accuracy guaranteeing safety in dirty environments, and the adaptive PID control tuned specifically for the nonlinear rheology of concrete.
That's absolutely right. The long-term strategic value here is immense. Manufacturers achieve mandatory compliance with Euro 7 and US ZEV regulations, yes, but they also gain a decisive competitive advantage in the market through operational benefits.
Silent, zero-emission operation dramatically improve product reliability.
And better concrete quality via that constant speed agitation, which reduces waste and callbacks for the customer.
The concrete mixer truck, thanks to this detailed engineering, is no longer just a clumsy piece of diesel machinery, it's an intelligent vocational terminal. And that leads us to the final provocative thought about the next engineering frontier. We've established the system can estimate concrete slump by monitoring gross torque. But what if we dive deeper?
Well, the control system is already collecting current and torque data multiple times per millisecond. The next step is utilizing that real-time current spectral data, looking at the micro-ripple analysis, to identify specific aggregate sizes, viscosity shifts, and material non-uniformity within the drum. The motor current signature holds the key to the concrete's internal secrets.
Imagine the possibilities. If an advanced control system, maybe using deep Q networks or AI, can leverage that constant stream of real-time material condition data, it can optimize the energy use profile moment to moment.
By constantly shifting the motor's working point on the efficiency map, it could even proactively adjust the drum speed to rehomogenize the mix, acting like an autonomous quality control officer. It shifts maintenance from reactive to precision, proactive science.
So a predictive model could identify, based on an anomalous current signature, that a batch of concrete is going to spoil miles before a visible problem occurs.
And allow the driver to correct it in transit with a small water or additive injection, saving contractors immense costs, preventing drum damage, and fundamentally changing how concrete is delivered and managed globally. The data layer, enabled by electrification, is truly the most exciting development in heavy-duty vehicles today.
Fascinating stuff. This system turns a construction site workhorse into a highly sophisticated mobile rheology lab. We'll be watching that intelligent vocational terminal closely. That's all the time we have for this deep dive. Thank you for joining us.